Hi, everyone. I'm Jasmine with the Building Performance Institute. Thank you so much for joining us today to learn about acoustic imaging. This webinar is brought to you by BPI, Surama, and the LEARN program. The LEARN program offers free energy efficiency and electrification courses, and they have an extensive list, so definitely check them out at sandiegolearn.com. And with that, I'd like to hand it over to Daniel and Willemijn from Surama.
Yes, thank you very much. Hi, everyone. Welcome. Greetings from the Netherlands. From wherever in the world you're joining us today, we're glad you could make it to our webinar. Please get comfortable, stay curious, and we can get started. We have quite a few exciting things to share with you. Today, we're going to talk about sound, not just as something you hear, but as something you can see, measure, and solve different problems with. Let's start with something we all experience, noise pollution. This slide shows just a few of the sounds we live with every day, like traffic, construction, planes, and if you're like me, a toddler who thinks it's party time at 5 a.m. Especially if you live in a bigger city, you've gotten used to these sounds, but that doesn't mean they're harmless. Our brains do their best to filter it all out, but our bodies still react by increasing stress levels, disturbing sleep, and even affecting heart health. Here's a video I took of a train while visiting the zoo, where I noticed how clearly the sound bounces off the concrete floor. And it made me think, in a city environment full of concrete buildings and floors, the sounds of cars, sirens, and jackhammers bounce back and forth. This constant reflection creates a soundscape where noise doesn't fade. This chronic exposure to noise, as already mentioned, impacts our health in many ways. And with all that in mind, you might be wondering, how loud is too loud? According to the World Health Organization, the threshold is about 70 decibels. As a reference, inside an airplane is about 80 decibels, which is already harmful for you if you're exposed to this level for a long period of time. It's also safe to say that sounds above 180 decibels close to your ears will cause permanent hearing damage. We often mention noise, and I just want to take a moment to explain what separates any noise, any sound from noise. We define noise as sounds out of place, an unwanted sound. Many of us assume noise is just any loud sound, but that's not always true. A waterfall, for example, can be very loud, yet it's not considered noise because it belongs in its environment. Now that you have this information, I want to test your knowledge. On this slide, you can see 10 different sounds, and I want you to vote whether they're considered noise or not. For your information, the videos are silent, so you'd have to imagine the sounds yourself. Let's start with the first example. Is a ringing bell considered noise? You can go ahead and vote. I'm gonna give you about 5 seconds per question and share the answer. A ringing bell is not considered noise. Moving to the second question, do you consider a squeaky office chair noise? Have 5 seconds to vote. Squeaky office chair is noise. What about drums? Drums are not noise. What about crickets chirping? Crickets chirping are not considered noise. What about a screeching fork? That's a pretty easy one. screeching fork is noise. What about confetti cannon? Moving to the next one, a confetti cannon is considered noise. Gym weights dropping, also an easy one. Gym weights dropping are noise. What about fireworks? Fireworks are noise. What about a loud geese army? Geese army is not considered noise. And the last one, train square wheels. Go ahead and vote. The square wheels of train are noise. And with this, I'm going to hand it over to my colleague Willemijn.
Yes, thank you, Daniel. So as you can see, I drew the short straw because Daniel got to play a fun little game with you all, and I get to talk about physics. Anyhow, jokes aside, sound works when a vibrating object creates waves in a surrounding medium, such as air or water. These waves consist of compressions, where particles are close together, and rarefactions, where they spread out. They travel outwards from the source, and when they reach your ear, they cause your eardrum to vibrate. And this is actually what your brain interprets as sound. When it comes to sound, it is very important to keep the medium in which the vibrations travel in mind, because it's molecules pushing against other molecules, like dominoes. The speed of sound changes depending on the density of the medium. As demonstrated in the visual, sound in air is actually quite slow compared to, for example, water. A question to think about while looking at this video, why do you think it's hard to localize an airplane based on its sound? It's actually because of the travel time of sound. By the time the waves reach your ears, the plane has actually already moved on. So we don't just hear one sound wave, but we hear many of them at the same time. Different vibrations have different wavelengths, and these wavelengths determine the tone of the sound. High-pitched notes have shorter wavelengths, and lower notes, such as humming, have longer wavelengths. And these also tend to travel further. On top of that, we also don't hear all of the sound waves around us. As humans have an average hearing range of 20 to 20,000 hertz. Below that range is what we call infrasound, and above that is what we call ultrasound. We can't hear it, but there's actually quite a lot of communication going on from animals in those type of frequencies. An acoustic camera is used to locate and characterize sound sources. It works by using beamforming to process signals from the multiple microphones and determine the location and direction of a sound source. By doing so, you can see where the noise is coming from, and this is actually quite similar to how our own ears localize sound. Sound travels via sound waves to your ears, and when it first arrives at your right ear and later at your left ear, you can localize where the sound is coming from. In our case, we need at least 2 ears to localize sound. An acoustic camera is even more precise because it has 64 and sometimes even up to 1,024 microphones. One microphone picks up the sound wave earlier than the others, and with a technique called beamforming, the location of the source is triangulated. The device then creates a colorful acoustic image over a camera stream as a visual aid, similar to how thermal cameras visualize heat. An acoustic camera literally lets you see sound.
Yes, thank you, Willemijn. To add to what you just said, I think the challenge with sound is that we hear it, but we don't always know where it's coming from. For example, recently I was walking in the forest and I heard a bird sing, but when I started looking for it, it was actually quite difficult to spot where the bird exactly was based on its sound. When we visualize it, on one hand, we add another sense to the mix because now you can see it, and we can also learn how it interacts with the space around us. By visualizing where reflections are and how intense they are, it turns sound into something we can understand and act on, especially in complex environments. Talking about visualizing sound, now imagine a stadium full of fans. Visualizing the sound during a game is used to engage fans by showing which sections are the loudest. It can be used for games like section battles or identifying the loudest fan. In fact, one of our US partners is already doing this. They track fan noise and link it to an app where fans can earn points that can be exchanged for tickets, drinks, or even free cheeseburgers. It turns fan sound into a reward system. Moving from stadiums to city streets, these technologies can be used to detect loud vehicles like motorcycles or cars with modified exhausts to enforce noise regulations. Visualizing sound is also changing how we study nature. Many animals, as Willemijn mentioned earlier, use sounds we cannot hear to communicate, like bats using echolocation to navigate, or mice using ultrasound to communicate. We've worked on bioacoustics projects with mice, pigs, birds, bats, bees, crickets, each with their own unique sounds. We just saw a few creative applications of sound visualization, but its most widespread application is leak detection. In industry, acoustic cameras are widely used to find compressed air and gas leaks. How it works? Imagine a tiny crack in a pressurized pipe that creates high-frequency sounds we can't hear, but acoustic cameras can pick up. This isn't only useful, it's essential because up to 1/3 of compressed air in factories can be lost through leaks, costing tens or even hundreds of thousands in wasted energy. Another key application is detecting partial discharge in electrical systems. These discharges produce unique acoustic signatures that show insulation issues in high voltage equipment. Visualizing these sounds help to prevent equipment failure and improves safety. Talking about safety, in environments that are dangerous for people, acoustic sensors can be mounted on robotic dogs, rovers, drones. They can autonomously navigate industrial sites, tunnels, or remote areas to detect issues without putting humans at risk. And now I'm going to hand it over to Willemijn.
Yes. So as someone with a background in industrial design, my favorite application is actually for product development. So let's say you are an engineer at Nespresso and you get the task to reduce the noise from this extremely loud coffee machine. And I think we all know which one. By visualizing the vibrations in your product, you can see exactly where the noise originates and how it travels through your product. This information allows for very strategic changes to the design in order to break the sound path and achieve significant noise reduction, so that us consumers can drink our morning coffee in peace. This is an example of a project that we've done with Giant e-bikes. They used to be the loudest e-bike on the market, but after using an acoustic camera, they actually became the most silent e-bike. Here you can see their situation without any adapters. If you look to the bottom visual listed above, no dampening. And we can clearly see a structural mode in the chain cover caused by the motor. And the first iteration, dampening was added, but if you look at the intensity of the colors, this only succeeded in changing the vibrational behavior. No noise reduction was achieved. The second iteration, however, did result in significant noise reduction. If you look carefully, you can still see the same vibrational behavior as in V1, but much less intense color-wise. Acoustic cameras have actually also been very crucial for the automotive sector due to the sheer amount of vibrations happening in a car. So you think of the driving axis, the motor, tire noise, but also sound leakages in the frame of the car. Luckily, sometimes we also get to have a bit of fun with our technology. For example, during the Glow Festival here in Eindhoven, where every year designers and engineers create interactive light art installations. couple of years ago, we participated by creating an experience that would create visuals underneath you when you make noise. And that is definitely something that you don't have to tell kids twice. We've experienced that firsthand. Lastly, there's also citizen science projects that allow to gain insight into the soundscape of a bigger region. Each year we organize the Noise Awareness Day, where we ask the public to make sound measurements with their phone in order to create awareness on noise pollution.
Yes, thank you very much. People often ask us if acoustic cameras can focus on certain sounds and ignore background noise. Actually, that's one of the key things they're designed to do. The three speakers you see in the video play at the same time at a different frequency, but we can choose which one to see. That's because the camera doesn't show all the noise around you. It shows the frequencies you choose as a user. That makes it possible to spot a quiet leak next to a loud machine. It can see the leak's frequency and ignore everything else. Okay, now let's take a short breather and summarize what we covered so far. We explored how sound visualization can be useful in nature, cities, stadiums, industry, and for inspections through robotic platforms, as well as product development. Now let's look at how this technology applies to the built environment. Buildings play a huge role in energy use and emissions. As you know, in the US, the building sector consumes nearly 40% of all energy produced and contributes 30% of greenhouse gas emissions. That's more than any other sector. A major step toward reducing environmental impact is improving how buildings are built and maintained. Improving the performance of a building starts with controlling air leakage. When it's not managed properly, it affects everything from comfort and moisture control to HVAC efficiency and emissions. As many of you know, the blower door test is currently the go-to method of testing how airtight a building is. It's great for meeting energy standards, comparing buildings, or seeing if renovations made a difference. But the catch is it only gives a general idea of how much air is leaking, not where the leaks are. Finding specific leaks can be slow and tricky. There are tools like smoke sticks, infrared cameras, tracer gases can help, but they all have limits like needing certain temperature or pressure conditions to work well. Today, we'd like to show you how sound visualization can be a useful method. We use it to spot leaks and gaps in buildings quickly and clearly. The idea is simple. To find leaks, we need to make noise on purpose. We play speakers to generate sound, which finds its way out through any fractures and cracks, same as how the air would escape. Then the acoustic camera registers these leakages and pinpoints the location. Here I have a short video for you to give you an impression of how a practical test looks like. On the opposite side of the door, we have the speaker generating sound. The sound waves penetrate through any openings, and we are able to visualize it with an acoustic camera. Probably you're wondering, how does acoustic imaging compares to thermal imaging? Here I have a side-by-side comparison. This is a newly built passive house undergoing the blower door test. On the left side, you can see how a thermal camera registers the air leak. And on the right side, you see how an acoustic camera registers the air leak. In some situations, we can even see that acoustic imaging can be a bit more sensitive. For example, here, the thermal camera registers the leak mainly on the bottom right corner of the window frame, whereas the acoustic imaging reveals the whole bottom slit leaking. So a combination of both tools will give you the best results. To summarize how acoustic imaging compares to thermal imaging, on one hand, you are not dependent on going through the hassle of installing a blower door equipment. The buildings can be tested throughout the whole construction process because you're not working with closed volumes. Right now, it's quite warm in the Netherlands, so a thermal camera will not work effectively. An acoustic imaging can be an option. You can verify acoustically whether the thermal camera leaks you're registering are not reflections, thermal bridges, or false positives, and you don't need an advanced training to use this technology. To test buildings with sound, you can use anything from a simple handheld Bluetooth speaker to a professional omnidirectional one. The goal is to make sure sound reaches all parts of the area you're testing. If you're using a less powerful speaker, it's important to move it around the frame to ensure full coverage. It's usually best to place the speaker inside the building because hard surfaces help reflect the sound outwards, which makes the test more effective. Depending on the situation, you can use sounds that people can or cannot hear, especially useful when testing in occupied buildings. Now let's explore some of the practical applications of this technology. In the next few slides, I will show you many different use cases on different types of buildings that I have personally measured. Let's start with the first one. As you know, windows and doors are usually the weakest points in the building envelope and contribute most to air leaks. Proper installation and quality control is crucial because even the most energy efficient windows won't perform if installed poorly. It defeats the whole purpose of investing in high performance windows. Without proper sealing around the frame, for example, air and moisture can easily sneak in and reduce the lifespan of your products. In addition to testing the installation on site, window and door manufacturers can benefit from the technology to make their products better. It can be used to test different sealants, insulation materials, glass thickness, and make very quick product iterations. Leaky skylights and roofs are a growing issue across Europe, affecting over 15% of the population. And when it comes to leaks, time matters. If ignored, even small air and water leaks can lead to serious damage. Older skylights often leak because of damaged seals. It's a useful application not just for installing new skylights correctly, but also for quickly diagnosing problems in existing ones before they get worse. Sound visualization can be a surprisingly powerful method for inspecting worn-out sealants, as there are currently no non-invasive methods available for testing sealants apart from a visual check, which is very subjective. This method is more factual and objective. Leaks in facade joints and corners are common issues in buildings, often stemming from material deterioration, improper installation, or design flaws. The first step of addressing the problem is identifying it. This is where technology can be useful. If a facade is not leak-free, apart from the energy efficiency losses, it might result in moisture issues, which is very expensive to fix down the line. In multi-unit buildings, smoke or cooking smells from one apartment can transfer into another through shared walls or ceilings, especially due to poor connections between the ceiling and the interior walls. If you're trying to diagnose the root cause of mystery smells in your buildings, acoustic camera technology might come in handy. It's also useful when testing how well individual units in a building are sealed off for better air quality, energy efficiency, and fire safety. Institutional buildings like healthcare facilities, educational institutions, or libraries and museums in Europe often face stricter air tightness requirements, especially when they are part of energy performance regulations or high-performance building programs. On this slide, you can see the results of a school building test in the Netherlands and the leakages we were able to find. In historic buildings, especially protected ones, traditional air leakage testing can be risky. Pressurizing the building with a blower door may disturb fragile materials, release dust from within the structure, or damage valuable furnishings. That's why acoustic testing can be a valuable alternative. It's completely non-invasive and works under natural, low or no flow conditions without needing to force air through the building envelope. This slide shows a test we conducted in a church where we were able to identify leakage paths without disturbing the structure or its contents. I imagine some of you might say buildings will always leak and there's always something to find. But if you've worked on passive house projects, you know the bar is much higher. These buildings are designed to be extremely airtight, and even the smallest leak matters. This slide shows the results from a test we ran on a newly built residential passive house. Despite it being freshly constructed, we found enough leaks that it didn't meet the passive house standard. Extra insulation and ceiling had to be added to get it over the line. So how can you inspect high-rise buildings? It's a question we often hear. A creative and practical solution is to use a drone. We can use its buzzing sound as a sound source. The drone's propellers naturally generate high-frequency noise, which acoustic cameras can pick up and visualize. This allows us to detect leaks around windows, facades, and joints in high-rise buildings. Unlike traditional methods that need sealed rooms and finished spaces, with acoustic camera technology, you don't have to wait for the paint to dry, so to say. It can be used throughout the entire building process, from early construction to final renovations, since they don't rely on closed volumes. They're perfect for spotting leaks and flaws before walls are sealed or systems are locked in. The technology can help detect leaks very early during the manufacturing of prefab facade systems, wall panels, and modular units to make sure everything is sealed properly from the beginning. However, they're usually tested when everything is clean, controlled, and precise. That's when airtightness looks great. But once these systems are installed on site, things change. Assembly in the field almost always leads to more air leakage. Sound can be useful during production to catch issues early, and later during installation to make sure quality holds up in the real world. Making high-performance building is just the beginning. Airtight buildings don't just stay airtight on their own. Over time, things like extreme weather or small seismic events can affect how well a building performs. With this technology, inspections can be done quickly and easily after such events. Regular checks help building owners, consultants, facility managers catch issues early and keep energy efficiency and comfort on track. And with this, I'm going to hand it over to Willemijn.
Yes, thank you. So sometimes it's not about reducing energy loss of the building itself, but about improving the well-being of the people that are on the inside. So occupational hygienists, for example, they are known to use this technology to get a grip on the noise on the work floor. This is actually an example from the Dutch Office of Unemployment. Inside of these rooms, very private discussions are being held with vulnerable people. So it's very important that whatever is said in there stays in there and not literally leak outside for everyone to hear. Being able to quickly improve the soundproofing of these rooms significantly impacts the comfort and trust of the visitors. Obviously, the technology can also be used to strategically place dampening materials on reflection hotspots, making sure that the room itself is pleasant to be in as well. It can also be about preventing unwanted particles, such as dust, from coming in, making sure that the inside stays as sterile as possible for sensitive equipment, such as in these type of clean rooms. Similar to increasing the comfort of buildings, manufacturers of these office booths that we all know utilize sound visualization to optimize the acoustic performance of these booths before they are placed in our offices. Sometimes going even as far to optimize the sound of the ventilation systems inside, ensuring that the noise inside doesn't disturb you from your video call. All in all, what all of these use cases have in common is that they provide you with clear and intuitive visuals that tell you exactly where the problems are and how to fix it. The visuals make it easy to communicate with contractors and suppliers, even without acoustic expertise.
Yes, thank you, Willemijn. To summarize, I think we've covered a lot today, from what sound really is to how visualizing it helps us understand nature, catch noisy vehicles, engage fans, improve products, and even make buildings perform better. I really hope you learned something new today. Now we'd love to hear from you and address your questions. But before that, I don't want to turn this into a sales pitch, but if after seeing our webinar, you're thinking, hey, this can be useful in my work, we'd love to support that. We can offer you a camera for $7,999, discounted from $9,500. To benefit from the discount, you can send me an email at daniel.giorev@sorama.eu saying that you joined this webinar, and we'll take it from there. And with this, I'm going to hand it over to Jasmate.
Daniel, if you'd actually like to go through some questions, that'd be great. It looks like we have quite a few in the chat. Did you want me to go through them?
No, we can go through them. Let me check the chat. All right, so we're just going to start from the top down and see how we do. Okay.
One of the first ones is, can it detect low pressure natural gas leaks?
Yeah, actually, we do have quite a few examples of natural gas leaks. You have whoever asked this question, you have my email. Please reach out and I can share more about that. But we do have quite experience with that.
And then there is another one about the app. It looks like everyone's interested in the app. If you don't mind talking about that again.
Yeah, I'm gonna give it to Willemijn actually.
Yeah, so we have a Sorama app. I believe it's currently only available in Europe. If you're really interested in the citizen science project, please also reach out to Daniel. But basically, it's the Sorama app, and we are still working on perfecting the calibration system there. Because obviously, a microphone in your phone is of a lot less quality than a professional microphone. So we are actively working on improving the accuracy of those type of measurements. Maybe it's good to add that on top of those acoustic measurements, we also have a survey that basically polls people on the experience that they have regarding the sound. So there's like, do you find this lively, or do you find this annoying? Those type of things that we also take into account when we make those measurements.
Great. And then another question is from Torrance. Are there combined IR and acoustic cameras?
I've seen some, but they work quite badly. Basically, you're getting a bad acoustic camera and a bad thermal camera in one. If you're looking for something high quality, you'd have to have it in a separate hardware.
Great, thank you. The next question is the acoustical camera an attachment for the iPhone?
I'm not sure I understand this question. I think people might be confused because in the front of the camera, you see like a little display like this. So this is not a separate phone. This is just integrated display. When you operate the camera, you control it, everything from here. So I would say, no, it's not attachment for the iPhone.
It's a standalone device.
Yeah.
Great. Can you output the SNR values you see from the camera?
I think so.
So the SNR, that really depends on the situation. So it's not like we can say this is the SNR that you have to have in order for our camera to pick this up. So what we notice is that's very situation dependent. However, we use MEMS microphones, so the bass level is 30 decibels, if I recall by heart. So that's the very absolute minimum that our cameras can pick up.
Great. And the next question is, if you were checking for ceiling leaks or floor leaks, do you have to put sound in those spaces for it to work? If so, can you put sound in one place, or do you have to move it around in the crawl space or attic?
Depends. Preferably, you'd want to place it in both rooms to ensure that sound reaches everywhere. Because if you put it in one room, some sound will reach the other room, but you're not sure everything is covered.
Thank you. And then Daryl's asking if there are financing options for the technology.
What financing options?
Are there financing options to pay for the acoustic camera?
I think like paying in separate instances and stuff like that. So currently we do not have those type of things in place.
Yeah.
Got it. And then Christopher's asked potential harmonics. Is that customizable or can it be calibrated in or out?
I'm not sure I get the customization part, but when we send it to someone, we calibrate it internally. In principle, you don't need to calibrate it anymore. It is possible that if you ask us, we will calibrate it for you, but it's not needed.
And the reasoning for that is because we use digital MEMS microphones instead of the analog microphones that have to be calibrated.
Great. Next question is from Stephen. How about ductwork systems? How would you verify if the ductwork is leaking or put sound in the ductwork?
Actually, some of our customers use this technology to check for leaks in sewage systems. So what they do is they put a sound source in the sewage system and walk on the other side and search for leaks. You can use the same principle. If you can put a speaker inside the duct, you will be able to see if you have any direct holes in the duct on the other side.
Awesome. And then Amir is asking, how can we categorize the leakage as either excessive or minimal? Are there specific benchmarks or thresholds we should be using to define this?
So the camera visually in real time can show you how many decibels are leaking from a specific spot. One way to quantify leaks is, let's say you're seeing two leaks at the same time. One leak is 30 decibel, one leak is 45 decibel. That will already give you some indication what the bigger leak is. Another method can be when you turn on your sound source, you know how many decibels you're putting out. Then when you're registering a leak, you can see how many decibels you're reading on the other side, and that will give you some indication on the leak size.
This can also be done on device, by the way. There's also an SLM function on device.
Yeah.
Great. And Shane's asking if you have any video demonstrations of use in retrofit construction.
Sorry, can you repeat this one?
Do you have any video demonstrations of use in retrofit construction?
I do have. Actually, this Tuesday, I went on site where they were renovating an apartment building and they wanted us to verify the quality of the renovations. Unfortunately, I'm not able to share that because of privacy reasons, but it has been used on retrofits. That's what I can say.
Great. Andre is asking if we can use this device to catch those small duct leaks, system leaks.
I haven't personally tested it, but as I earlier mentioned, if you're able to put a sound source inside the duct, and if you have any leaks, you will be able to see them on the other side.
Great. Falabi, sorry for mispronouncing that, is asking if they can get the data recorded from the camera to see the SPL values in an Excel table.
I think you can do that through the portal.
Yes.
Yeah. So the short answer is yes.
Yeah.
Awesome. Jeffrey's asking if the volume what are the volume levels of the speakers used?
Well, that depends on the environment you're testing in. So if you're testing in a silent environment, normally you want to play about 10 decibels above your background level. It can be 60 decibel, it can be 95 decibel, depends on the situation. But what's also interesting to mention, you might be asking this question because if you're testing occupied buildings, you don't want to be disturbing people with loud sounds. You can also play high frequency sounds very loudly that people cannot hear, but pets might be able to hear and still not disturb occupants.
Great, thank you. Nick is asking if you can quantify the size of the leaks.
Not in terms of airflow. We can quantify it in terms of decibel. So we can give some idea which are the bigger leaks, but we cannot related back to airflow yet. We are currently researching that.
Great. Dale is asking if the camera comes with a speaker.
No. We just sell the cameras. As I mentioned, you can use any simple Bluetooth speaker. We can give you advice on what equipment you can get, but this is something you have to find separately.
Thank you. And Amber has a question about industrial applications. Would you be able to detect mechanical anomalies in conveyor motors and bearings? Is that
Yes.
still dependent on the RPM?
So basically what we do is in our industrial business unit, we can definitely detect acoustic anomalies, but we can also with AI and classification, we can do predictive monitoring basically. So we can see when things are beginning to break. So yeah, that's definitely one of our applications.
Thanks, Willemijn. Ross is asking, can the acoustic camera be used during a blower door test while depressurizing a building to identify air infiltration points? Or would the noise from the blower door interfere with the camera's effectiveness?
So if you're asking whether the camera will be able to see the air leak from the blower door test, that's not the case. You can turn on a sound source that's a separate frequency range from the blower door fan in a way that it doesn't interfere.
Great. Stephen mentioned just showing the outside of a building where air is coming out is good, but it doesn't show where the root cause of the air is coming out from. So can you put the sound on the outside of the house and then check the inside of the house exterior walls?
Yeah, for sure. As I mentioned, we prefer to put the sound source inside because then all the walls help reflect the sound and push it outside, but it's perfectly possible to switch it up.
Great. Larry asked if you are hunting for a water leak under a slab, how do you know what frequency to shoot for initially?
Yeah, the frequency doesn't matter. You can look for any frequency. The challenging thing about water leaks is that sometimes the path is very complex, where the water enters and where you actually experience the water leak and the maze between it. And in some situations, sound is just not able to pass through the whole maze. But if you have a direct path of the water leak, in that situations, it can be useful to diagnose.
Great. Is it possible to detect moisture contaminated insulation in roof or wall systems?
Sorry, you cut off. Could you repeat the question?
Is it possible? Yeah, sorry. Can you hear me okay now?
Kind of. I'm looking for the question in the.
Is it possible to detect moisture contaminated insulation in wall systems?
I don't have enough knowledge about how moisture contamination works. Do you have an answer?
I don't have expertise on this, but just reasoning wise, I would say if there is water damage but no straight sound path, we won't be able to detect it. So I think it depends on the amount of damage, basically.
Yeah, if you with some of our acoustic cameras, we can detect vibrations of the wall. For example, if you have a water pipe passing through the wall and the water sliding through the pipe, when you make a scan of the wall, you can be able to visualize where that pipe is. If the moisture contamination causes some holes or something that can be acoustically different from the rest, let's say when you excite the wall, you might be able to see some differences, but I'm just assuming here.
Great. Can you still hear me okay?
Yes. Yeah, now it's good.
Great. Stanford asked, you mentioned placing sound source inside the ducts. Could the air leaking out of the connections be detected by the camera?
So if we're talking about just the air leaks without any sound source inside, I don't think we're going to be able to detect that, because it really depends on the pressure with which the leak is coming out. So this is also why when we're talking about finding air leaks, we are talking about compressed air leaks. So pipes that are under pressure where the air leaks are being pushed out.
Great, thanks, Philomene. What are the ideal decimals we should be looking for?
I'm not sure what is meant by ideal decimals here. Do you understand it?
No, so I think basically you are in control of the sound source. That's also one of the the key parts here of this method, is because you actually know the sound source that you put on one side, you actually know what to look for on the other side. So the ideal decibels there, that's really what Daniel said earlier. It's dependent on the situation. You have to be above the background noise in order for the camera to be able to detect the leaks.
Yeah, and a very easy way to answer that is just before you turn on your sound source, look at how loud it is. For example, in this room right now might be 60 decibels. I want to turn on my sound source at 70 decibels at least.
Thank you. Kevin asked regarding duct leaks, perhaps similar to the e-bike assessment, as the air leaks are making noise.
That will not be feasible, because the air leaks we are talking about, for example, in industries, they are in very, very high pressure pipes, and that's what produces the noise. Ducts don't have big enough pressure to be able to visualize it with sound.
Great. Jeffrey asks, could you use the camera on a wall with no leaks to determine the areas of the wall that are internally transmitting more or less sound?
That's actually a application for one of our more advanced acoustic cameras. So for example, we do this a lot in super yachts, actually. So then we can actually trace the vibrations that are being caused by the motor. They're being passed onto the floor, and then they become structural. And with our acoustic, more advanced acoustic cameras, we can actually visualize the structural vibrations, and then we can follow them inside the walls as well.
Great. Christopher has a two-part question. The first part is, how is the camera able to differentiate between target frequencies and potential harmonics? And the second part is, can you calibrate those harmonics into or out of the detection?
Yeah, so our devices also give you real-time spectrum and spectrograms on device. And basically, you can use that to make a selection. So what you will probably see if you have a rotating instrument, you will definitely see the harmonics. They will pop up as individual peaks in the spectrum and the spectrogram, and you can decide to just focus on one of those, so either the base frequency or one of the harmonics. When it comes to leak detection, I would advise focusing on the higher harmonics, because the higher frequency you visualize, the smaller the blob actually gets, and the easier it is to pinpoint the exact location of the leak.
Great. Robert asked, what is the detectable audio frequency range when using acoustic imaging technology to locate and pinpoint air leaks?
It can be, so normally the signal we use is between 20 hertz and 20,000 hertz. The actual frequencies we are normally of interest range between 6,000 and 18,000. That gives you a nice range combining relatively low and higher frequency, that you're still able to visualize it with high precision. Yeah,
I do want to add on that, because when it comes to beamforming, and so then localizing the sound, it depends on the size of the array. The bigger the array, the lower frequencies we can visualize, because like I explained just now, the blob becomes bigger, and at some point you will just see an entire red screen. So it depends on the size of the array, what the lower frequency bound is for beamforming. For these handheld acoustic cameras that we have shown you in this presentation mostly, the lower frequency bound is roughly 500 hertz. But here's the catch: if you want to use it for leak detection, you are in control of the sound source. So you can definitely go, you can make a sound source that is of a higher frequency, and therefore it's easy to visualize, basically.
Great, thank you. Nick is asking, what is the frequency range of the microphones?
The microphones itself, they can pick up from 23 hertz up until 23 kilohertz. But that's only for the spectrum and the spectrogram options. So the beamforming, like I said, again, that's from 500 hertz and up, depending on the size of the array.
Yeah, and also good to mention, although these are the limits of the individual microphones we use, the microphone array, the actual combination of all microphones, that performs better than the individual microphones.
Yeah, that's also true.
Awesome. Vernie is asking, with just a blower door setup and running, can the camera pick up sound with just air coming through a crack?
I think we already answered that. No, because the pressure is not big enough.
Great. Another question is, would it be fair to say the acoustic camera is better at detecting leakage issues than insulation issues?
It can detect both. I would not say it's
Awesome.
better. Yeah, would you?
So I would say it's better. So this is a discussion that we will have later on. Better as in it's a lot easier to interpret leakages than it is to interpret the insulation issues, because obviously we can still measure, like we know what's outside and we know how much of that comes inside, and so we know how well the insulation is working. But when it comes to the visualization of that, obviously with a leak you can just pinpoint, oh, that's where a leak is, and with insulation it's a lot less visual, I would say.
Yeah.
So that would be my interpretation of that.
Great. What is the cost of the spherical speaker array, and what frequencies can it produce?
This is not an array, this is a speaker. So do we know the cost of that?
This is about 2,500 or 3,000 euros. Not sure how the exchange rate is today.
So this is not something that we ourselves produce.
Yes, but this is the most high-end sound source you can get. You can get started with something simple for $100 to $100.
Awesome. William is asking, what are the advantages and disadvantages of acoustic versus thermal imaging?
Well, right now in the Netherlands, thermal imaging will not work because you don't have big enough temperature difference. The benefit over thermal imaging is that you are not dependent on the blower door equipment, so you don't have to pressurize the building. It's a lot more practical to use. You can just turn on a sound source, and within a few minutes, you can already start measuring with an acoustic camera. Yeah, do you want to add anything?
Nope, I'm already reading the next question.
All right, we're going to answer just a couple more questions. So Javier asked, how can acoustic imaging data be combined with AI to predict air leak risks and guide proactive maintenance?
So this is also what I explained earlier. Basically, we make a benchmark. If we do continuous monitoring, we make a benchmark of the basically the soundscape, and then we listen to very small changes in the soundscape, and then we can actually train our model on that to tell you what those changes mean.
Great. Is there a catalog of camera and accessories?
Yes, email Daniel.
Yeah, email me.
We'll go through just a couple more questions. Does any existing sound, music, passing vehicles, etc., affect the readings?
It can, but again, it depends on the frequencies you're visualizing. For example, let's assume you are testing a building next to a busy highway. What you can do is you check your spectrum and you see which frequencies are present in my background. And then you try to play frequencies outside of that range to improve the signal to noise ratio and the effectiveness of your test.
Great. And the last question we're going to go through is from Kimberly. Is this a purely qualitative analysis, or are there quantitative conclusions that can be drawn?
It's mostly qualitative. There can be, I guess, by quantitative conclusions, you mean actual air leakage rate. That's not something we can say yet, but we can say something about whether it's a small, medium, or big leak based on its decibel mark.
Great. If your question wasn't answered today or you have more questions, we talked Daniel's email in the chat today, so please feel free to email him back again. Daniel and Willemijn, thank you so much. You don't mind sharing your screen again so I can just close out real quick?
Yes.
So in the meantime, thank you all for joining us, and thank you again to Daniel and Willemijn for all of your insightful information. We would love to hear your thoughts and feedback on our webinar today, so feel free to submit them by scanning the QR code or clicking the link that I just tossed into the chat. So we'll give it a minute just to pull out your phone and scan that QR code if you'd like. Awesome. And then next slide, please. If you are interested in receiving a BPI CEU, please send us an email at ceus@bpi.org with your name and ID number. So go ahead and take a screenshot of that or take a picture with your phone to save that information. And while you're doing that, I just wanted to mention that we also have another webinar coming up that will explore how energy efficiency measures can support improved indoor air quality, indicators to measure, and how monitoring and ventilation strategies can balance energy savings with occupant health. So if you'd like to register that, please scan the QR code and lock the spot. And as you are all for all the information, thank you so much for a great webinar and have a great rest of your day. If you have any questions, feel free to reach out to Daniel and Willemijn.
All right, thank you all for your attention, and I hope you learned something.